Hello and welcome to our lecture on beamforming. This is a continuation to the previous lecture. So first of all, in the last lecture we talked about plane wave transmissions. We also talked about focus transmissions. It turns out there is another way which is relatively popular, which is called synthetic aperture imaging. So what is synthetic about this synthetic aperture imaging? Let's understand that. Typically when you are performing imaging, you need a large aperture to get good imaging resolution. Why is that? If you remember, there is a Fourier transform relationship between the aperture function and the pressure profile at the focus, right? So if the aperture is large, it turns out that the profile at the focus will be narrower. That will give us better spatial resolution, lateral resolution to be specific, right? So in synthetic aperture imaging, we synthesize a large aperture. What do I mean by that? Typically, a large aperture is not available or not practical. So we synthesize a large aperture by moving a smaller active aperture over a large array. Essentially what we do is, so look at this transducer where there are these elements here. So what we do first is we fire with one element, which is shown here in red, but the signal that comes from the scatterer is received by all elements, which is shown here. So signal is coming from the scatterer, it is received by all the elements. Now I'll fire with the second element and I'll receive with all the elements, and similarly I'll continue till I fire with my last element and receive with all the elements. Now this gives me, let's assume that we have 128 elements here. This will give me 128 low resolution images. But I can combine the signal from these 128 low resolution images to get a high resolution image, which will be my synthetic aperture image. Why is that? Because when I combine all those images, it is almost like using the entire aperture at a given time. So that is where the synthesis of the aperture comes into the picture. This is different from linear array imaging because in traditional linear array focus transmits, we only use a small aperture or a sub aperture relative to the entire aperture. But in this case, we are using the entire aperture, although in a synthetic fashion. So here is an image which I took from this open access paper from Lim and colleagues. Here are some point targets and they are imaged using the traditional way, using focus transmits with 10 elements, and this is focus transmits with 25 elements. And you can see the point spread function. So here the points are further stretched out. It's a little bit better when you increase the aperture size because you have 25 elements now. Because these points are better localized compared to this one. As you can see here, the geometrical extent of the spread is more, but here is relatively tighter. So bigger aperture is good. But when we apply synthetic aperture, this is a variant of the synthetic aperture, but still good for discussion sake. What you see that the points are localized extremely well. The points are not very well spread in the lateral direction. They are not spreading much, which means the lateral resolution is good. The point spread function is narrow. And these authors also performed imaging of the eye. So here is an example of the image taken using the standard approach versus the linear array approach. And I don't know if you can see it clearly in your computer, but here the image is much sharper. You don't see some clutter signals that are visible here. The boundaries are much clearly defined. That is because synthetic aperture gives you better spatial resolution. So let's discuss and summarize the advantages and disadvantages of this synthetic aperture approach. It gives you good lateral resolution. It gives you enhanced depth of field. Why is that? Because of dynamic focusing. We will discuss that later. Now using this synthetic aperture imaging, even if you have a smaller probe, you can synthesize a larger aperture. So it compensates for the lack of physical aperture. You can improve the signal to noise ratio and also to an extent reduce the speckle because of this averaging. The only challenge with synthetic aperture imaging is that it is data intensive. For n transmitting / receiving elements, you get n square A scans. So this n square is a large number. You need to store this data and process this data, and that is what makes synthetic aperture slow. And also, when you sequentially activate each channel and wait for the signal to reach all the other channels, the time taken because of the intervals between firings, the time taken to capture one image is longer for synthetic aperture imaging. Now let's delve into this process of beamforming. So focusing is also a type of beamforming, but here we are talking about bringing the signals in phase. So far we have just discussed it conceptually. I said that we provide delays and then using those delays we bring the signals in phase. But here let's discuss the exact process. So in delay and sum beamforming, which is a very traditional form of beamforming, most commonly used because it's fast, what we try to do is, if we have a signal from a scatterer, right, then there will be lack of coherence in the signals received. So this is a point scatterer. It is giving out this spherical wavefront, because of which the signals received by the center element will be first and the peripheral elements will get the signal at the end or later. So what we see is that these signals, if we try to sum them up, they are not going to combine coherently, or in other words, you won't get constructive interference. So if we want to actually have them sum up in phase, then we have to give them some delays. So the least amount of delay is given to the center element, because this is where the signal arrives first, and the highest amount of delay is given to the peripheral elements. Now the signals are aligned, and then you can sum and you get a strong signal here after delay and sum. So what did we do? We did a process of providing delays, then we sum up the signal, and you do this for each pixel at each location, right? So you got what is called delay and sum beamforming. It turns out that delay and sum is not the only beamforming approach. There are several other advanced beamforming approaches as well. The challenge with delay and sum is it uses geometry. So what it does is it just computes the extra distance that is to be traveled for the signal to reach a particular element relative to the center element, right? But this assumes a uniform speed of sound, or the speed of sound being constant in the entire tissue volume, which is not true because our tissue is inhomogeneous. Luckily, there is not a huge variation in the speed of sound, as you may remember from earlier lectures. There is only a small percentage difference, but that is enough to cause some errors in delay and sum beamforming. So that is where some advanced beamforming approaches have been proposed, which give you better resolution and better SNR than delay and sum beamforming. One of them is delay, multiply and sum beamforming, in which a multiplication step is introduced, wherein before you combine the signal, so I will go back to this one. Let's say instead of summing all these signals like this, I am going to create pairwise multiplications. So I am going to multiply these two pairs, these two pairs, these two pairs. Like this, I am going to create pairwise multiplications, and then I am going to sum. So what does this multiplying pairwise achieve? It turns out that when you multiply pairwise signals, it enhances the constructive interference from signals that are in phase, and such signals are originating from the same source or direction. So they will be fairly similar. Essentially, they will have a high correlation amongst them, and when you multiply them, the signal will increase. But if they are coming from different sources, there will be limited coherence. So when you multiply them, the signal will not increase to the same extent. And therefore, this approach is able to reduce the effect of noise and off-axis signals in the reconstructed image. So if you have an array where the array elements are not equally sensitive, there may be some difference in element gains, or let's say one of the elements because of some physical damage is only half as sensitive, then the reconstructed image using standard Capon beamforming will be very noisy, sometimes even imperceptible. But robust Capon beamforming has some additional constraints or penalty terms in its optimization process, which makes it robust to such variations in, for example, the array response or the position of the array elements, where there might be some variations relative to the theoretical positions. So robust Capon beamforming has been researched a lot. There is a plethora of papers that are available in literature. It is still not that widely used because it is computationally intensive. But nonetheless, with growing computational power, I think very soon its use will increase. Okay, now let's discuss dynamic focusing. So, what do we mean by dynamic focusing? It turns out you can do dynamic focusing in transmit as well as in receive. So, here is an example where you have a linear array and I am firing it in a focus transmit mode. I select a bunch of elements and I fire, and that creates a beam, and this beam will have a certain profile and it will focus at a particular depth. Now it turns out that if my region of interest looks like this and my beam looks like this, it will have the best resolution here, laterally speaking, but poor resolution here and here. So what can I do to fix it? Well, this is where dynamic focusing comes into play. So instead of focusing at this point, by changing the delays or by changing the number of elements that I am using to fire, I can focus at different depths, right? Okay, so now if I have a region of interest here, I can choose to focus at different depths by firing again and again. First, I focus at this depth, so now the best resolution is here. Then I focus at this depth, best resolution is here, and then I focus at this depth, the best resolution is here. Now if I compound all these images, if I add them together essentially, then what's going to happen is my resolution is going to remain good with depth. And that is shown here where we have 3 transmits. So the first beam has a depth of focus at depth 1, the second beam has focus at depth 2, and the third beam has focus at depth 3. And when you combine them all, you don't get a very significant degradation in the lateral resolution as you move down. So this is called dynamic focusing, and the challenge with dynamic focusing is that you have to fire multiple times. So this is in a sense constrained, but there is also something called dynamic focusing on receive, which is used even more frequently. So here it turns out that the signal that is arriving from a particular depth. So let's say this is my grid over which I am trying to reconstruct my image. This is my grid. And I choose any pixel, right? So to reconstruct this pixel, what I am going to do is I am going to look at, this is my transducer. Let me draw it with a different color. I am going to look at the geometry, and I am going to look at when the signal is going to arrive at all these elements, and then I am going to bring it in phase so that it sums constructively. And I am going to do this not only for this pixel, but for all the pixels. So that means that this pixel is in focus. Later I reconstruct this pixel because I am bringing the signals in phase. This is also in focus. And likewise, all the signals that are emanating, they will be in focus. Every single point in the grid will be in focus. So this is called dynamic focusing on receive. And this is just a post-processing thing. You don't have to fire again and again for this. That's why this is used very frequently. And by doing this, we are able to maintain good resolution with depth by using dynamic focusing. Okay? So like is written here, in simple receive focusing, the transducer is more sensitive to the signal coming from the focus, and the resolution is dependent on the beam width. But in dynamic receive focusing, the beam width is minimum at multiple axial depths, and therefore the lateral resolution is also better. So now let's change track a little bit and let's talk about beam steering. So beam steering refers to changing the direction of the beam We have discussed very briefly about this in the beginning lectures. So the idea is now if I change the phase of the signal emanating from individual array elements, I can cause the beam to tilt. So I'll give you a physical example. I think you would have done march past at some time in your school days, probably for a parade. And if you had a group of people standing like this and marching ahead, so let's say you have these people standing like this and marching in this direction. Say if you wanted to turn right, how would you do that? Well, you could start walking a little slower if you are standing on the right, and the person who is standing on the left starts walking with faster and faster speeds, and then essentially your wave front or the front of your group tilts and starts going in this direction, right? So you have changed the speeds to change direction. Now it turns out in our case we cannot really change the speed because the speed of sound is dictated by the properties of the medium. But what we can do is we can move some things faster and slower by applying delays. So by applying an angular delay profile, I can make the beam tilt, right? So why do we like to do this? The reason is sometimes we have a narrow acoustic window, right? For example, if you are looking through a keyhole into a room, you want to scan the entire room, but you are looking through a small aperture, which is the keyhole. So you are going to steer your eyeball from left to right and top to bottom to cover the maximum volume which you are able to see. So similarly here, the idea is when you are looking through the ribs or some narrow acoustic window, you would like to get the maximum field of view by steering the beam. So beam steering can not only steer the beams in different directions, but it can also focus in certain directions. It can change the angle as well as maintain a focus, but it requires phased array transducers. We will discuss more on that later. So here is an example where these are the transducer elements, and this is x of 0, the center elements, this is x of m, and this is x of minus m. So if we give a delay profile where the center element gets 0 delay, x of minus 1 gets a certain delay, and this is the delay profile. Delay keeps increasing with the elements. Similarly, here is also a delay profile. So then we get an angle at which our plane wave gets steered. Now this is a plane wave, but we can also add some additional delays to create focusing, which will generate a focused plane wave. So for this example, if I simply want to tilt by an angle of theta, the delay of the nth transducer element, so starting from this x0, the delay is going to be xn sine theta by c if I want to tilt by an angle of theta, and c is the speed of sound. So it turns out this electronic steering is effective only in the near field of the array. In the far field, it does not do a great job. So typically here, if you have a pitch mu in your transducer, pitch is the size or essentially the distance between two transducer elements from the center to center, then the distance should be less than this quantity or the Rayleigh distance to be able to steer effectively. Now here it's shown how you can have a plane wave steered in a certain direction, but you can also create a focused wave. So linear delay profile creates a plane wave at a certain angle. If you also provide a concave delay profile on top of that, it's just geometry. You have to compute the angle at which you want to fire. The combination of this creates a focused steer beam. Now, creating focused and steered beams helps us in better imaging resolution because focusing improves lateral resolution, which would otherwise have looked poor because of lack of beamforming if it was a simple plane wave. Now let's discuss a confounding factor called grating lobes, which creates artifacts. So if you have the elements of the transducer with pitch of mu, when they are simultaneously fired, you will get constructive interference in certain areas. Now the condition for constructive interference is, if constructive interference happens at a theta angle, then sin theta is n lambda by mu, where n is going to be 1, 2, 3, etc. For higher values of n, constructive interference happens not only in the center direction but also in some other directions, which can create other focal spots apart from the desired focal area, and these secondary interferences create artifacts called grating lobes, and it can also be thought of as a spatial undersampling. So in signals and systems, we know that if we don't follow the Nyquist criteria while sampling, we get something called aliasing. We get these artificial frequencies. So similarly here, if we think of this grating lobe as a spatial undersampling, if the elements are not close together, that is lambda spacing for linear array and lambda by 2 spacing for phased array, then you get grating lobes, which we will see in the next slide, and that is because of spatial undersampling. So here we see the main lobe. Here is the main beam located at a 0 angle, and at an angle of 10 degree you have another grating lobe, at an angle of 20 degree you have another grating lobe, right. So this is because this is a linear array, but the inter-element spacing is actually 6 lambda, wherein it should be less than lambda, it is actually 6 lambda. So therefore, versus angle I am getting these grating lobes, right. So just to remind you, for linear arrays the pitch should be less than lambda to avoid grating lobes. For phased arrays, pitch should be less than lambda by 2 to avoid grating lobes. Now if I follow the criteria where I choose a pitch which is less than lambda for linear array and less than lambda by 2 for phased array, what happens to the grating lobes? One can argue that sin theta, sin being a periodic function, there will be some constructive interference beyond the main lobe, right. So where do the grating lobes go? It turns out that if you undersample, the grating lobes point forward. So essentially my transducer is this and it is imaging in this direction. This is my region of interest and my grating lobes fire in that region. They are in my region of interest. But if I sample properly, it turns out that if my array has dimensions such that the element dimension is less than lambda for linear array and less than lambda by 2 for phased array, it turns out the grating lobes will face backwards. They will be at an angle where they will not really contribute to your image. They will not create any confounds. So let's summarize what we have learnt in this lecture. We'll continue a little bit more on beamforming in the next lecture as well. But here today we discussed synthetic aperture imaging. We discussed delay and some beamforming conceptually. We discussed some data-driven beamforming approaches such as robust Capon beamforming. We discussed some other advanced approaches such as delay multiply and some beamforming. And we discussed dynamic focusing, which helps us to improve the resolution versus depth. We discussed beam steering for narrow fields of view, applications such as cardiac imaging where we use this beam steering to get images. And lastly, we discussed grating lobes. So I hope you found this lecture interesting, and I'll see you in the next lecture. Thank you.